Good afternoon, everybody. Welcome to class today. Thank you for joining me, whether you're watching live or you're watching the recording. I appreciate you watching. Thanks for joining me this afternoon. So just as a reminder, right off the bat here, when we do these live classes, we're doing them a week ahead, right? So Module 1 is due this coming Thursday. If you're looking for Module 1 material, please go back to last Tuesday's live class and watch the recording from that. Today we're looking a week ahead into next Tuesday, or next Thursday, right, when Module 2 will be due. Right, so in Module 1, which we talked about last week, we were just kind of dipping our toe into the idea of writing some code with Python. And today we're actually going to kind of get into more about the programming part of everything with variables, expressions, and statements, right? So we're getting started at kind of the very beginning, conceptually with programming with our most basic data structure, which is a variable, and then things to go inside of those data structures, which are expressions and statements. And this is all going to kind of expand on and build on the kind of stuff that we were looking at last week. So as we are talking about Module 2, one of the first things that we want to do is we want to define some terms here, and we want to define the term variable. What is a variable? And so when we're thinking about a variable, we're basically thinking about a container, right? Got a little Tupperware, some kind of container here on the screen. But that's really what we're thinking about when we're thinking about a variable. Some kind of container, right? So we can kind of look and see, okay, well, we got a container here, we got a box, we got something going on here, right? So here it is. It's the middle of January. We just left the Christmas season a couple weeks ago. Some people may still have their holiday decorations up. But many of you, if you had some holiday decorations up, by now you've probably taken them down, right? And when you go to put your holiday decorations up or you go to take your holiday decorations down, you typically have some kind of container to store those in, some kind of tote, or a big box or a big bag that you put all of your holiday decorations in. And on that box or bag or tote, you write some kind of label and you stick it on there. That way you know that when you go looking for your decorations or whatever it is that you're looking for, right? Maybe you're looking for old baby clothes, or maybe you're looking for old photographs, or whatever it is, right? If you have it stored away in some kind of box, you put some kind of label on it, and then that label tells you what's inside of that box. And so a variable kind of works the exact same way, right? It's this same sort of analogy that we're working with here when we're working with this idea of, okay, I'm going to store things in this box, and then I'm going to put a label on that box. So let's say we put a label on this box here, and we're going to give that box a name. Right, we're going to give that box a name. In this case, we just call it vary for variable or whatever. Right, and then what happens is this name on this container basically gives me a named spot in memory, right? So this takes and reserves out a little section of my computer memory, gives it a name, and allows me to put data in there, right? So I can put data into here, and whatever data I put into there is then associated with the name that's on the container. Right, another way that I like to explain this sometimes, right, is if, like, let's say you're going to tell somebody you're coming to Cleveland Community College. Right? Well, Cleveland Community College is an entity. Cleveland Community College has a space in the world. It has a position in memory, right? It takes up physical space. Just like your data in your software takes up physical space on your hard drive or in your RAM or whatever you're working with. But whenever you refer to Cleveland Community College, you don't necessarily refer to all the pertinent data surrounding what you need to do, or where exactly you're going to. Like, you don't tell people, oh, I'm going to the Paxoy building at 137 South Post Road, Shelby, North Carolina, 28152, right? You know, the whole address of the college. Right? That's a bunch of data that is in this physical space, that is in this bit of memory, but we don't refer to it that way. We refer to it by the label that's on the container that holds all this data, which is Cleveland Community College, right? So we just tell people like, hey, I'm going to Cleveland Community College, and then they know where you're going. They know what you mean, right? So I can go and I can put data into one of these containers, and that's a reserved location in memory that has a name on it. And then when I make reference to the name of that reserved location in memory, I can take that data out and I can use that data. All right, so any structure where we're holding any kind of data, we call that a data structure. There are a bunch of different types of data structures in programming. A variable is one of them. We'll talk about arrays and dictionaries as we move on through the course. In some more advanced courses, if you continue on to university computer science courses, you might talk about things like, you know, linked lists and stacks and heaps and all this sort of stuff, where it's just, you know, different things that just hold data in different ways, or that allow you to interact with data in different ways. And so this is the most simple one of those, because it's just a container. We put data into it, we take data out of it, we put a little label on that container so we know what we're dealing with here. Another thing to think about is that Python is weakly typed, so we don't have to worry about declaring a variable type. Some other, like, you might hear people refer to as weak typing. You might hear it referred to as loose typing, or what's another word that's often used? Like dynamic typing, dynamically typed. Because like one of the things that we looked at last week, right, is when we're writing code in Python, we said that we don't make a promise to our computer that data is going to be a certain type of data like we do in, say, Java, right? Many of you are also in the Java class this semester, so that'll be, you know, a challenge as we're looking through or working through strong versus weakly typed programming languages. Python can just kind of figure it out for us, right? So it knows that if I have a variable and I say I want to put this line of characters that's in quotes into that variable, then it just makes it into a string variable dynamically. That also means that, you know, it kind of does this on the fly while you're working with it. So you can take, say, an integer value, a numerical value out of a data container and replace that value with a string, right? And it's going to work just fine in the same container. There's not really a whole lot of a purpose in doing that generally. There are some niche times where this becomes incredibly useful. But in general, like, we're just using one data type in one variable container. We don't want to really use the same container for too many different types of data, because if we do that, then we lose that data that we could need, right? Remember that, you know, this variable is basically a memory storage location. And so if we take data out of this memory storage location and we throw it away and we replace it with new data, that data that we've thrown away is gone, right? It's just dissipated as heat, right, out of our processor. So that data is not coming back. We're not getting that data back. So we want to be able to understand that, like, we need to make intentional decisions when we're replacing the values that are in variables. So when we look at variable creation is technically a two-part process, although it is not in Python. Right? Because we said Python's dynamically typed or weakly typed. So whatever kind of value we put into that container becomes the type of that variable at that given time. So if we were working in, say, Java, right, one of the things that we would do is we would say, oh, is that we could say, oh, well, I'm going to make a little integer variable here, and I'm going to call it whatever, like let's call it, for the sake of this, stack height. And if I'm in Java, I can throw a semicolon right there at the end. And then what's happened is that I've created this memory storage location and put the name on it, stack height. So now I have a little box in my computer memory that's labeled stack height that I can put data into later, and it's reserved. Right? And so my computer can do this because it knows what kind of data to expect, and it knows what I want to name that data. And so in Java as well, like one of the things that we discuss in that class, if you're in that class, you've seen it at this point, right, is this idea that these different data types also have memory values associated with them, right? So if we use an int, like we're looking at in this case, the primitive int in Java reserves 4 bits of memory or 4 bytes of memory, I should say, 4 bytes of memory, which would be 32 bits of memory. That's what it reserves to kind of let that information live in there. But in Python, right, we don't have those constraints, right? Like, we're not saying, okay, this is going to be an integer variable. We're not saying that an integer variable has 4 bytes of memory that it automatically reserves, right? Because my interpreter and my Python interpreter is going to do that automatically, dynamically. So we're kind of reserving a little bit more space on the off chance we need this bigger container. And so in this case, we can't do like we've done here for Java and say, okay, well, I've created this container now, and then later on I can put some sort of value into that container. In Python, it's basically just this second part here. So in order for me to know what kind of size that container needs to be and what's going into it and what's kind of being built with it, I need to be able to have that value there to give my interpreter that context. Because otherwise, right? Otherwise, it's not going to know what to do. It's not going to know how much memory to reserve. It's not going to know the data type of the memory that's going to be put in there, because it would basically just be the variable name. In this case, it would be stack And let's do it with PEP 8 rules here. Height. Right, so that on its own doesn't give my interpreter enough context to know what kind of memory to reserve here. Because one of the things to remember, kind of takes us back to last week, right, is this idea that Python's not its own thing, kind of sitting out there on its own. Every programming language has kind of been built on other programming languages. So you see, like basically as programming languages progress, they're just kind of built on top of older programming languages. So you see that Python's built off of C, which was built off of assembly, which is built on, which is just, kind of goes back to machine code. Right, and so on and so forth. So since it relies on C to make these things, C does need to know a data type. It does need to know a container size in order to reserve this memory. So we need both of these parts here. Now, when we look at declaration, right, declaration is where we name our variable. And in Python, we assign and declare at the same time, right? Declaration is where we name our variable. Assignment is where we give it a value. So declaration is where we create the container. Assignment is where we put a value in that container. Now in Python, as we just discussed, we have to do both of these at the same time. We have to name the variable and put a value in the container simultaneously. And as a result, right, one of the things that becomes super important to us as we're writing Python is this idea that our variable names are super important, right? Because, we can name them whatever we want within certain restrictions. The variable names can be as long as you want them to be. They can be mostly whatever you want them to be, which we'll see on the next slide here, how that changes in certain contexts. But you can make the names as long as you want them to be, whatever you want them to be, but typically we say they should have some meaning to them. They should be meaningful so that you kind of know what you're talking about when you go back and look at your code later, right? Like, I know, like, you'll even probably see me do it sometimes where I'll go in and I'll just put, X for a variable name. Just because I'm trying to do something really quickly and just show it out there, and I don't really, have time or want to take the time, I should say, to pick a good variable name. So I'll just throw something in there like X. But then when we look at the program in context, X doesn't mean anything. So if I hand the program off to somebody else, or I go away from it for a weekend and then come back to it, I might wonder, like, hey, what did I mean by this? What does this mean? So the name that we choose is important, and it should kind of give us an idea of what kind of data is in this variable, even though we don't have to declare a data type. The name should give us an indication as to what's going on with the data. Now, there are some other rules here. Like, one of them is there are some rules that we have to follow, and there are some rules that we should be following. Right? The rules that we have to follow are thus. Variables cannot start with a number. When your computer sees a number, it thinks it's about to do math and it gets excited. Right? You might have a weird friend or something that's excited about doing math. Well, if you consider your computer a friend, your computer would be then your friend who's excited about doing math. So when it sees a number, it thinks, oh boy, I'm about to do math. Here we go. Math's about to start. But then it might see a letter, or it might see a symbol. So then it gets real bummed out, right? Because it thought it was going to do math, and then it's not doing math. So we can't put a number at the start of our variable name. Variables cannot be a reserved keyword. Now, a reserved keyword in any programming language are words that are already used in the program or in the programming language. So I believe I have some of these I believe I have all of them in the module if I recall correctly, but I'm just pulling up the list here really quickly just to show them. Right, things like false and true and import and return and while and with and finally and break and for, right? These are all words that are used otherwise in the Python programming language, right? They are words that already have a meaning within the Python programming language. So we can't try to give them a new meaning by assigning them a new value to a variable. Right? Like all of these words already exist and they already do something. So none of these words can be used as variables. Another thing is that variable names are specific, right? So remember, it's like what we talked about last time when we looked at ASCII values, right? We said that our computers, they don't care one bit about words, right? A computer can't really read, right? A computer can just interpret patterns. Remember that whole thing? So if you use a variable that looks like, say, this, and it's all lowercase p, lowercase I, and then you try to refer to that same variable later and you refer to it in all uppercase p, and uppercase I. Remember that we, as smart human beings, we know that that's the same word, right? That's just pi, and that's pi twice. But to our computer, that's two totally different things, right? Because it goes back to that ASCII chart, all the stuff we did last week. To get us to where, we're kind of understanding these concepts. There are also PEP 8 naming conventions. PEP stands for Python Enhancement Procedures or Python Enhancement Protocols, right? Either one, it's fine, right? Like you might hear different people say that it stands for different things. But these are just general rules, just general guidelines and best practices for how to write Python code. And so this kind of gives you the look of how some things look in Python. So while what we saw on the previous screen, right, like if you break one of these variable naming rules, breaking one of these variable naming rules will break your program and cause it not to run. If you don't adhere to PEP 8 naming conventions, it'll just look a little different compared to other programs written in Python. And specifically when it comes to variables, we use lowercase characters, right? We can use a single letter, word, or multiple words. And when we separate multiple words within a variable name, we use an underscore to kind of connect those two words together, right? So in other programming languages, the convention might be to, when you hit a new word, you start that word with an uppercase letter. This is called camel casing, right? So we'd see something like, if we did that stack height thing, it would be stack height. With the uppercase A in the word height all together. And so this would be camel case. This would be something like what you see in JavaScript or Java. In Python, we would separate these with underscores. And this is called snake case, which is appropriate, right? Because it's Python. Python uses snake case. So let's just do a little code demonstration here as a means to kind of talk about some other stuff. Usually what I do here for this would be to do something kind of similar to the style of whatever you would use to do your lab for the module. And again, we're talking specifically about module 2 here. And so what I usually like to do for this one is I like to talk about volume of a cylinder as my example for this. So volume of a cylinder, right, is V equals pi times radius squared times height. So pi times r squared times h is typically the overall calculation for it. And now one of the things that you'll see me do as you'll see me approach these problems is you'll see me kind of overcomplicate them a little bit. And I'm not really overcomplicating them. Right? It looks like I'm overcomplicating them because if I'm being honest, to a certain degree I am. Right? Because you could just go in here, create a singular variable that would almost look like what we did here. And just say that like V equals 3.14 times 3 squared. Let's put that in parentheses so it uses my PEMDAS rules times 5 or whatever, and that's going to get me my outcome. But then again, what happens to all the data that we have from these numbers? It goes away, right? So we lose some of that flexibility of being able to say, like, well, what if we wanted to use the same numbers and do the surface area of the cylinder? Or what if we wanted to use the same numbers and do whatever, right? We would lose that ability if we just put everything into one equation and then just printed that out. All that work is just lost as heat to the air around it, nothing stored in memory. So we'd rather not do that. So in order to start off this program, what I'm going to do here is I'm going to add our shebang, right? Remember, we talked about the shebang last time. All of your programs should have the shebang. And I'm going to do something here that's going to be called, that we call composition. Composition is when we basically take a big problem and we break it down into little parts. This allows us to hold more data in memory so we can be more flexible in using that data to solve other problems that we might be presented. And it also allows us to fix problems when we find them. So what I might do here, right, is I might say, well, let's create a variable for our pi value. That's going to be 3.1415159. Right? A little single precise floating point number here that we're going to use for our pi value. Then I can create a radius value. And set it equal to something. And I can take a height value and set it equal to something. right? And this is super useful, right? Because now I have these containers carved out in memory. They have a value in them. So now that value has a symbolic relationship to the name of that container. And so if I were to start to expand on this, I could do something like radius squared and set that equal to the value of radius to the power of 2. Right, so now I don't have to go through, right, every place where my radius is used in calculations. If I want to change this radius value, I can just change it here in one place. And in future modules, when we start to introduce inputs into the equation, I can just put an input here and let that cascade down and be used everywhere we need it. And so really now I have all the values that I need kind of stored in memory to perform this calculation, right? I have my value for pi stored in memory. I have my value for radius stored in memory. I have the value of radius squared stored in memory, which is going to cover that whole piece of my equation. And I have my height stored in memory. So I can create a volume variable that would be pi times radius squared times height. And another thing here that's kind of cool is I don't have to worry about my PEMDAS, my order of operations, because this part of my order of operations is already done. Because I've calculated it previously and stored it in a variable previously. Which is pretty cool, right? So now I know that I can print out the value of volume, and that's going to give me the answer to my equation. Which is pretty cool. And one of the cool things about this actually is that one of the reasons why we kind of use some of these problems as means of getting us started is that it's really easy to kind of check our work, right? Like if I wanted to type in volume of a cylinder, it's going to take me to Google here, and it's going to give me the ability to test my work, basically. And so if I put in a 4 for a radius and a 7 for a height, we can see I get here from Google, the program that's already been done for me, 351.86. And my value is 351.85808. And my value is essentially the same. It's just a little more precise, right? Which is pretty cool. And another reason why, again, we'd keep all these is in case we wanted to solve another problem. So let's say we wanted to add that whole surface area, the thing that I talked about. Right? So if we look at our equation for a surface area is 2 times pi times radius times height plus 2 times pi times radius squared. We already have all of these problems. And we already have all of these little bits of data saved in our program. Aside from the magic numbers, the constants here, the 2's. And so I can just make a surface area variable and set that to 2 times pi times radius times height. And we can just put some parentheses around that. And add that to 2 times pi times radius squared. Right, so now I have all of this stuff here. It's already all been saved in memory. I don't have to evaluate it again. So since I kept all of that instead of letting it go, I have the ability to reuse it. And I can print surface area as well. So we can run this. We can see our results. 276.45992. If we look here, we can try this as well, which would be 4 and 7. 276.46 versus 276.45992. Right, again, more precision for us. And if we want to change these values, now that we know that these values work, we can just change our radius to make it something more complex. Our height to make it something more complex, and we can have relative confidence, right, that our outputs are going to be good. Right, we're going to know that those are going to work, basically. Question from the chat. So in this case, right, I think Christy, I think this is kind of what you're asking, is that, you know, what the name really means in the grand scheme of things, right? So the name really means nothing. It's only kind of telling me what it means. Because remember, like, these words, they don't mean really anything to my computer. Right? If I wanted to, I could come in here and I could say, well, this isn't radius, really. This is Apple. And I could change everywhere that just said radius to, say, Apple. And I'm going to get the exact same results, right? Because these words, they don't mean anything to my computer. They mean things to me. So that when I'm going through here and I am writing this code, I know what I'm looking at when I'm doing it. Right, so it's on me to name the variable. It's on me to put the item in the calculation wherever it needs to go. Because none of this really specifically means anything to my computer, right? Like the word radius doesn't mean anything to my computer. It can be anything in this context. But, like, if I'm working on this and then I go away on vacation, right? And then I come back 2 weeks later and I look at what I was doing and I say, well, what did I mean by Apple? What does that mean? It doesn't mean anything. Right? It doesn't make sense to me. It doesn't make sense in context of the program. It might have made sense to me at the time I wrote it. But without naming the variable something that actually makes sense in context of the program, it'll still make sense to my computer. It just won't make as much sense to me, because remember that I'm the one that words matter to. not so much to my computer. So I think that might help answer your question. If it doesn't, just throw something else back in the chat there, and I'll try to clear things up a little bit. And I was probably a little bit late on picking that up. And I do know that there is a little bit of stream delay here as well. So we'll kind of pause just a second here. But that is a good question. And at the end of the day, right, like the big thing to remember is, cool. Wonderful, wonderful. Thanks so much. Thank you, thank you. So now I have this program. I've got this one program. It's not entirely flexible enough to what we want it to do yet, right? Like, we're going to add some tools to our toolbox over time so that this program's actually more flexible. But I do want to kind of flesh this out a little bit, right? Because we can see some things here that maybe don't make as much sense to us, right? Because on our output, we see that we have two numbers here, but we don't really have labels for those. And so one of the things that we talked about last week was the concept of operators, right? And mathematical operators. And we said that we use these mathematical operators on numbers. So I can say things like 2 plus 2, 9 modulo 2, 9 modulo 3, 4 divided by 1.7, 3 times 13, whatever, right? Like, we looked at all of these different mathematical operators: plus, minus, multiply, divide, floor division, modulo, and exponent. And we said we use these with numbers to do calculations, right? But then we also talked about strings, right? We said that, a string is basically, when I take quotes and put them around characters, then they're not numbers anymore. They're characters, they're strings, right? Like, if you look on one of those ASCII charts like we looked at last week and you look at the number 2, the number 2 is the character 2 on the ASCII chart. So it represents something like 50, I think it is, on the decimal value, which breaks down to something like 0, 0, 1, 1, 0, 0, 1, 0. Something like that, which isn't the value 2 for doing math. Whatever it is, right? It's not the value 2 for doing math. And one of the things that we said was, our computer likes doing math with numbers, but we can't do math with words, right? Like, we can't say like eggs over easy here as a funny little pun, right? Or third time's a charm. Like, that doesn't quite work. There are two exceptions though, and one of them is the plus sign operator, and the other is the multiplication operator, right? But when we use these with strings, they're no longer the plus sign operator and the multiplication operator. They are the concatenation operator, and they are the repetition operator. So the concatenation operator allows me to take two things and put them together, right? So I can take two strings and put them together. I can take a string and some numbers and put them together. So if I looked at it in context with like our program here, I could add a string in this print statement that says something like volume, VOLUME, colon space, and put a plus sign there. And that will take those two and kind of stick them together. Right, now notice this space here, right, between the colon and the closing quote. Remember that a string, the letters in a string don't mean anything into my computer. So if I want to see a character on the output, I have to put it in my string somewhere. We can do the same thing here with our surface area. And now we have labels for these values. And so if we run this now, whoops, that is something to remember, is that concatenation is for strings, right? So we would need to typecast these values into strings to use them. I'll show you all another way that you can do this as well. I believe we looked at this a little bit last week, right? We looked at the data type and we said, like, hey, you know, if you want to change data type from one thing to another, right? So now we have that all working. We can just wrap that in a little string typecast, which is str, open close parentheses, surrounding our number. Changes it from a number into a string of characters. Another way that you can do that, right, is to just use a comma. And this is a very Python specific way, which is why I don't really like doing it this way. But I can just put volume, comma, our variable name. And that's going to work. Which that's a very Python specific way of doing it. There's another way to do it in Python, which is called an F string, which we'll talk more about a little bit later on. I'll just go ahead and put these in here just so we can kind of see them. But in an F string, I put an F inside of my inside of the parentheses in my print statement here. And then I can just use a set of curly braces to denote my variable, and basically just kind of spell out everything as if it was part of the same string, right? And these F strings are something that we'll talk about a little bit more later on in the course. Once we get into some more complex problems, because they do make writing outputs for complex problems a little more simple. But for the time being, since I am going to give you all a link to this code, I'm just going to comment them out. So they're there for you to reference, but they won't run. All right, I think we talked about comments briefly last week as well. Right, we said basically that if we put a hashtag at the front of a line, it turns it into a comment. That means that my compiler ignores it. I can put it at the front of a whole line like I'm doing here on 3, 4, 16, and 18, or I can put it after a line of code like that there, and it's just going to ignore this little part until I hit enter on my keyboard. And that just helps me provide some more context, right? And again, this context is to me, right? My computer is ignoring that part. So another thing that we might want to do with string operators is we might want to do a little bit of repetition, right? We might want to take the same string and repeat it multiple times. One of the things that I'll use this for a lot would be to like make a little decoration to create a pattern. I might say, oh, let's create a pattern variable here. And I'm going to set that equal to a string that's maybe just some emojis. Right, so I'll pull up my emoji keyboard here and I'll just put a few robot heads in here. Now, what I could do is I could take this one robot head with these two spaces, and I could copy it and I could paste it as many times as I wanted it to put it in there. But that's going to be a pain. And what if I want to change how many robot heads that I put in there? If I want fewer robot heads or more robot heads, I have to, copy and paste more or delete some. It's just going to take me longer. So if I want, say, 5 robot heads, I can take that string and I can use my multiplication operator, which now becomes my repetition operator, and just put in there how many times I want to use it. And that's going to repeat it 5 times. So if we printed pattern, we'd see that robot head symbol. Used 5 times. And if I wanted, and if I think, oh, 5's too many, let's change that to 3. I can just go change that value, right? Now it's 3. So then we can use these two things together to kind of make us a cool little program title here. So maybe I want to concatenate that with, say, the phrase cylinder solver, and then put that same pattern in there again, right? Because I could still just go back to that same container, get that same data, bring it back again. And now we have a cool little title for our program. That has a little bit of flair to it. And if we want to change how many robot heads, we just go change this number after our repetition operator. Instead of having to copy and paste. And then we have more robot heads and we can kind of play with it accordingly, right? It's a lot of fun. And so we've just about hit our hour for today, which I don't usually like these going any longer than an hour. So I want to talk about the different types of errors here really quickly before we go. And while I'm kind of talking about these different types of errors as a part of our debugging, if anybody is here with me live that has any questions, feel free to drop them in the chat. Remember, if you're watching the recording at home, feel free to send me an email or a Teams message with any questions that you may have while you're watching this. Again, as you're watching the recording, I recommend taking notes. I recommend trying to work along with me when I'm doing these demonstrations. I recommend pausing and rewinding and going back and watching things again and again if you have trouble or you don't quite follow as you're watching the recording. So there are 3 main types of errors. There are other different types of errors, but 3 main ones that I want to talk about right now. These are our syntax error, our runtime error, and our semantic error. Right? And a syntax error basically just means that we broke the rules of how the structure is supposed to be written. Right? So, we talked about the idea of syntax last week, I believe. And we basically said that syntax was basically just like how we have rules in English. And we say that, we're supposed to start our sentences with an uppercase letter in English, and we're supposed to end them with a punctuation mark. And if we have multiple thoughts, then we have to separate them with commas and so on and so forth. And if we don't follow one of these rules, we get a syntax error, which is going to break our program. Right? It's going to break our program immediately. And one of the good things about Python, and that's one of the things that you kind of look at in your experimenting labs, is that these syntax errors are usually pretty specific to tell you how to fix them. I think along with the next module, we look a little bit more about syntax errors. Right, but you saw a little bit earlier when I forgot to typecast my integers into strings. It gave me that little error, and that was a syntax error. And so it kind of told me exactly where my problem was, and I could go back there and figure it out. A runtime error is an error that happens after the program has started running. These are also called exceptions, and they usually indicate that something bad has happened in the execution of your program, right? Like it's either ran out of memory, or it's hit some weird calculation, or something weird has happened that's caused the program to crash. Right? And you can kind of think about this in terms of, say, a car, right? Like if you get in your car and you turn the key in the ignition or press the button, depending on what kind of car you have, and the car doesn't start, that's a syntax error. You got a syntax error somewhere, right? Like there's something not quite right on the car that's kind of broken that needs to be fixed before it'll run. A runtime error would be like if you got into a car crash, right? So things are kind of going along, and then all of a sudden you run into something. And so like this is also kind of, of course, like it's overly dramatic, right? But this also kind of goes into like how big the problem could be, right? Because when we think about how widely used programming is nowadays and how it's basically in everything, right? There's issues, there's programming in banking, there's programming in healthcare, right? And so, if your program doesn't start at all, then somebody has to figure out how to fix it, and that might delay things. But if your program is working and, say, controlling an artificial lung, or maybe doing some sort of pacemaker or some other sort of healthcare device, and then all of a sudden there's a runtime error and it crashes and stops working, then that's a whole new problem. Right, and the third type of error here is a semantic error, which is related to meaning. And with a semantic error, another name for a semantic error is also a logic error. It basically just means maybe you misunderstood the problem, or maybe you didn't quite do the calculations correctly. So it's running, and it's working seemingly fine, but it's giving you the wrong answer. Right? It's doing something that maybe you didn't intend for it to do. And so these are our three big types of errors that we talk about, just to kind of wrap up today. And that is where we will stop for today. We're about 45 seconds from hitting our hour mark, so we'll go ahead and wrap up here. If there are any questions, throw them in the chat, and we'll go ahead and answer them. Otherwise, I want to thank you for watching today. If you're watching the recording, send me your questions via Teams or email. We'll hold for just a couple seconds here for any live questions that may be out there. I'll send you this code when I send you the recording of today's session. So you will have access to this code. Just real quickly, just because I saw some issues in another class, don't uncheck public. I need public to be checked for this to run, or for me to run it. So if you've already turned in module 1 stuff and you unchecked public when you turned it in, go back into that program in CodeHS and recheck it. Otherwise, I can't see it. I'll put out a separate announcement to that effect, just to remind you all, probably tomorrow as well. So with that being said, and seeing no further questions, that's all that I have for you for today. Thank you for watching. We'll see you next time.